Hi everyone, my name is Ivan and I'm going to be presenting Apex, a verified architecture for proofs of execution on simple embedded systems. And the settings we're looking into in this paper are those composed of cyber-physical systems and IoT systems where a higher-end, more sophisticated device controls low-end, simple embedded systems that implement sensors and actuators. So you can think of several examples as the ones in the figures. And the problem with these settings is that even if we succeed in securing the higher end device, the controller, this device still relies on the sensor, which is implemented with the low end embedded system. So it relies on the sensor to report that everything is okay when everything is okay. But if something bad comes up, it relies on the sensor to also tell the truth and say that something bad is going on. And the problem is that if the sensor is infected, what happens is that the malware that infects the sensor can say that everything is okay, even though the sensed value is something else. Right? And if we look at the sensors and how they're implementing using low cost, low energy, small size microcontrollers. These are devices such as the MSP430 or the ATmega32, which is used in Arduino, and they have few kilobytes of program data memory, slow single core CPUs, and they're very resource constrained. So they're very, very challenging to secure. And with this kind of devices, we have a problem at hand, which is how to trust the results or data produced by such a simple embedded device that could be compromised. And can we bind the produced results to the execution of the expected software? And finally, can we do this cost effectively? Even if all software on the device could be compromised, can we still provide some sort of security? So what we want in the end is a sensor device that even when under the possibility of compromise would always tell the truth. So let's look at how the sensing process works on a microcontroller like this. And it typically involves some trusted software that will interact with a digital hardware or an analog hardware, and will execute a sequence of commands that will trigger the sensing or actuation process through this what is called general purpose I/O, which is nothing more than specific regions in the device's memory that are hardwired to the physical ports and therefore can communicate with the external world. And in order to make sense of this sensing process and to make sure that it is doing what it's supposed to do, configuring the sensors or actuators and reading or writing the proper results to this GPIO, we need to make sure that the proper code is indeed executed, so we need a proof of execution. And if we look at the related work on how to secure the software state of embedded systems, we see that it typically involves something called remote attestation, which is a two-party interaction between a trusted entity, a verifier that will be the controller in our cases, and a prover that's a potentially compromised low-end cyber-physical system IoT device, which is our fire sensor in our example. And the goal is to measure the internal state of the prover. So there are several examples in the literature and really many remote attestation architectures in the past, being proposed in the past 10 years. And if you look at the remote attestation interaction, it happens between the verifier and the prover, and it looks a lot like an authentication protocol, a challenge response-based authentication protocol, except that the prover doesn't authenticate itself. The prover authenticates the contents of its memory. So the prover would receive a challenge and compute a signature or a message authentication code over the challenge and its own memory and send the result back to the verifier. The verifier can then check if this corresponds to the expected value of memory. So if the remote attestation architecture on the prover is secure, and there's a deep meaning to what secure means in this case, but we're going to skip it for this presentation. But if it is secure, it should provide an unforgeable proof that the prover memory corresponds to a given value at the time of the remote attestation computation. So it seems like a natural path to use remote attestation to build sensors that cannot lie. However, remote attestation by itself is not sufficient. It doesn't prove that the code that's been attested was executed, and it doesn't bind the outputs of this execution to the code. It just tells you that the code is in memory. So if we want to, try to use attestation to achieve this, what we could do is we attest and then we execute, and then a compromise could happen in between the attestation and execution. The reverse is also true when you execute and then attest. And even if you attest, execute, then attest, you could have a compromise after the first attestation and the device healing itself before the second attestation, causing the attestation to result in a benign setting, even though what executed was not the proper code. And the takeaway is that remote attestation by itself is insufficient to prove execution of the expected code, and we need something more. With that in mind, we introduce what we call the proofs of remote software execution, or POX, which is a cryptographic binding between the executed code, any outputs produced by the execution of this code, and a temporally consistent remote attestation of the same code, meaning that the outputs and the code that executed could not have been changed in between execution and attestation of the code. And in doing so, we must be mindful of the low cost, low energy, small size requirement of this low-end devices and the possibility of full software compromise, which implies that we're gonna have some hardware support. So with that in mind, we propose APEX, which is a formally verified architecture for proofs of execution. And the idea is that with cost in mind, the simplest thing we can do is to set one bit. And we refer to this bit as the exec flag. And minimal formally verified hardware in APEX controls the value of this bit. And when it's 1, it indicates that the attested software indeed executed properly. And when it's 0, it indicates that it didn't execute it, or this execution was tampered with. This flag is stored in a specific physical memory address, and this address is covered by the remote attestation execution. Therefore, assuming that the remote attestation is secure, we should not be able to forge a response that contains any value that we want. Therefore, the adversary is unable to lie about the exact flag value. And with that, the problem of proving execution is reduced to controlling the exact value. But before we go into what we do, what does proper execution mean? In the context of this work, we mean that the executed code runs atomically, meaning it's not interrupted, and it runs from its first legal instruction until its legal exit, or its last instruction. This execution happens after the receipt of the challenge, meaning that's a timely execution. Otherwise, you could just replay results of previous executions. So in the case of the fire sensor, you could replay that there's no fire when there is fire. And finally, neither the executable nor its outputs are modified. So let's look into APEX design. In the right, we have the attested memory. This is the memory range that will be covered by the attestation procedure. And the gray part of it consists of what we call metadata, which is a set of physical addresses reserved to store configuration parameters about the execution that will be proven. And it includes the exact flag, which has the behavior I told you before, and a location for storing the challenge that is received from the verifier on each proof of execution request. It also includes pointers defining the output region, the region where the output of this execution will be stored, and defining the region where the software that's going to execute is located as well. And APEX works by monitoring these values and also monitoring several CPU signals, such as the program counter, the data access bus that tells you which data is being accessed at a given time, and others. And with this, APEX defines the executable, the exact value. And before execution, this metadata must be configured according to the execution we want to prove for. So it must be written beforehand, including the challenge that must be received from the verifier. And once its execution starts, it cannot be changed, because the change will be treated as a violation, as it could be an attack. And we trust that this configurations will be written by untrusted software on the device, because if it isn't, the proof of execution will fail, and the verifier will detect that it wasn't properly written due to the attestation security. So during execution, what happens is that initially the exact flag has value 0. This is the default value when the device boots or after a reset. And the only way to set the exact flag to 1 is by going into the legal entry of the executable, meaning that the program counter has to point to the first instruction in this range. And as I said before, it should execute atomically. So if there's any interruption, or if the device resets or anything like that, it will cause the exec flag to go to 0. If DMA actions are performed in parallel with this execution, it will also set to 0, because it could be tampering with the output result or with intermediate data memory values of this execution. So it makes exec go to 0. And the takeaway is that the only way to leave the execution of this ER range is through the last instruction, the legal exit of this code. So this is the only way to keep exec 1. And the caveat here is that this implementation of this code should be aware that it should write any outputs to the OR region to make sure that they are covered by the attestation results, so that the outputs are also bound to the execution. And after that, an honest prover that wants to prove execution is done. It just attests this figure that we have right now in memory. But the malicious guy could try to do more things in between execution and attestation. It could, for example, try to modify the executable to convince the verifier that this result was produced by the execution of some other code. It could try to change the output to spoof the result. It could try to change the challenge in metadata to reuse this proof of execution for multiple challenges, therefore triggering replay attacks. Or you could change the regions that define the output and the executable, and the effect is similar to that of changing the executable and the output itself. So if any of these things happens, Apex sets the exec value to 0. I don't have time to go into the details, but I want to comment on Apex formal verification, which is a large part of this work. And it's basically the effort to try to formally specify every property that I mentioned here in high level, such that we have a precise specification for the meaning of these things. And once we formally specify it, we can actually use a computer to check if the implementation of this hardware module corresponds to these properties. Once we have this verified hardware module and the formally specified properties, we can also use a theorem prover to use a computer to check if this property is implying some more meaningful notion of security. So we actually specify all the sub-properties that I described here in a formal logic called linear temporal logic, and we check the hardware implementation for compliance with these properties using a model checker called NewSNV. And finally, we ask the questions if these properties are enough to imply secure proofs of execution. And we show that the conjunction of these properties imply this definition 5, which I'm not going to go into the details. And this definition, in conjunction with a secure remote attestation architecture, implies secure POX, or secure proofs of execution. Finally, we did implement Apex using an FPGA, and we used it to build this fire sensor that cannot lie that I mentioned in the beginning of the presentation. Everything is available on GitHub. And we evaluated this architecture, showing that it's reasonably affordable. It's 12% more lookup tables and 2% more registers on top of the remote attestation architecture of raised. It's relatively inexpensive compared to other attestation techniques that give attestation of runtime properties such as control flow attestation. And with that, I will conclude the presentation. I'll be happy to take any questions.